The topic of today's lecture is integrity constraints. The integrity and consistency of a database is of prime concern to any designer. That is, the database should be correct and consistent as per the requirements of the designer at each and every point of time. What do we mean by consistent and what do we mean by saying that the database should be correct? This means that all the relations should satisfy the conditions which are normally supposed to hold on those relations. Now, these conditions are specified in a number of ways. These conditions are specified by the attributes, that is the type of the attributes, what is the exact type of the attribute. If the attribute is of character string and you start putting in some date type characters, then it's fine. But if it's of date type and you put in characters strings A, B, C, D which are alphanumeric characters, then it does not go in with what the database is supposed to be defined. Secondly, these constraints have to be checked again and again at every point when you do insertion, deletion, and any modification or updation of the database. So, these are the three important places where checking of consistency is required: insertion, deletion, and modification. Every time you add a new element, you have to check whether it's of a particular type, whether the relationship is 1, 1, on 2, 1, 2, whatever the relationship has been defined, that has to be checked. And we have to check whether the primary key or the key attributes are really working as key attributes or they are working as anything else. Second, checking of consistency is required in another case. It is required during recovery from failure. Whenever the system fails, power off, disk crash, and so many other things, the database which is there must be recovered to a certain extent and must be consistent with the situation. That is, if you say that the train reservation system has got corrupt, then every day during power off, then it will be a very funny situation all over the country. The second thing is consistency during concurrent operations. We have discussed this before. When 2 or 3 items insert, delete or update shared data, when they read shared data, there is not so much of a problem. But when they insert, delete or update shared data, then there is an added consistency problem which occurs due to the racing conditions. The problem which is similar to that of working on shared data in operating systems, the similar problem will appear here. So, all these consistency checks have to be made during the operation of the database. But in order to make these consistency checks, the database designer must provide a mechanism so that what are the consistency checks that have to be done, what are the constraints that have to be checked, these have to be specified. So, at a certain point of time, we need tools or mechanisms for specifying the integrity constraints in a database management system so that checks can be made effectively. Effectively means here two things. One is they can be made correctly, so that you, in spite of all other things that go on into the system, we really can correct the error or we can detect the error. So one is detection and correction, and the second point is of effectively is efficiently. So any database management scheme must have mechanisms to specify the constraints that must hold in a database system, and must be able to check this, that is, we must be able to detect or correct the error, and we must be able to do so as efficiently as possible. Therefore, the topic of today's lecture, and for some of the few lectures that will go on from now, will be to study the formal tools that have been developed for specifying and using these integrity constraints. We have seen some constraints before when we looked up at the entity relationship model. In the entity relationship model, we have seen that during the specification of an entity or a relationship, we specify several other things. Firstly, for every attribute, we specify, for every entity, we specify the attribute types. Other than anything else, we specify the attribute types. And we specify for every entity what are the key declarations. When we specify something called a primary key or a key of an entity in an entity relationship model, we mean that in that entity set, no two tuples can have the same key, same values corresponding to the key attributes and different values corresponding to the other attributes. For example, if we pick up the entity corresponding to a book in our library database system, we have the entity corresponding to a book. Here we had three values. One is the accession number, one was the year of publication, and the third was the title. We had specified there that the accession number is the primary key, which means that any two entities in this entity set book, if they have the same accession number, the other two attributes must be identical. That is, this being same, these two must be same, which effectively in this particular situation means there can be no tuple. There can be, in this entity set, there does not exist two tuples which have the same accession number. Only one tuple with that accession number will exist. That was the first one which we saw. So key declaration immediately helps us to identify what are the primary attributes and what are the attributes which are to be checked. And once we know what are the key declarations, we will always be able to detect if there are two elements which have the same primary key in the database. Two tuples cannot exist in a database in a particular entity having the same primary key value. So that check can be made at every point during insertion and updation. That check need not be made during deletion. The second interesting constraint which we saw was the cardinality constraint. We saw that a relation may be 1-1, a relation may be 1-many, a relation may be many-1, and a relation may be many-many. For example, in our database, we had the book, the user, which had the attributes borrower name, borrower address, and card number, and this entity had got a primary key and we had the relationship borrow, which had its own attribute date of issue, and the cardinality constraints could be specified by marking arrows here. And if we said this is one to many from this side, then we would have to say that a particular book can be borrowed by more than one user. At least that for every element here there can be more than one element here. If we say it is one to many from here, then for every element here there can be more than one element here. But for the same element here, this is one to many. If it is many, then two entities can participate in more than one relationship. And if it is one, then we will mark it like this and say that for one book only one user, and for one user only one book. Now, once we specify constraints like this, at every time we modify this element of the database, we can immediately check whether this constraint holds or not. If this constraint does not hold, we say that this constraint has been violated. So, using the ER diagram and using the cardinality constraints, we can provide a more specific definition of the database, and we specify those things which can be checked during every insertion deletion, so that the consistency of the database is maintained. Another type of integrity constraints which we saw in the ER model was the concept of a weak and strong entity. A strong entity was one which could have some elements which are not mapped to any other element in any relation, whereas a weak entity was an existence dependent one which depended on a strong entity for its existence, in the sense that every element of the weak entity would have to be mapped to some element of the strong entity. And using this, we could define certain constraints on the entities and check them during every operation. And now deletion comes into the picture, because whenever we delete an element from the strong entity, we would have to check the weak entities to see that any weak entity has lost its existence dependence on the strong entity or not. So that should not happen at any point of time. For example, if account number is dependent on the branch and we suddenly delete the branch, you cannot have an account number at a particular branch of a bank and you have deleted the branch of the bank itself, that branch itself from the bank database. So that would make it inconsistent. So in the ER model, we did have a number of such specifying techniques by which we could specify the integrity constraints. In the relational model, it is even more powerful, because now we have at our disposal expression of relations. We can express any relation. We can say that we can provide any predicate saying that this attribute plus that attribute must be less than some other attribute during any operation. In a particular relation, we can always mention that we can write down a predicate which checks that for the account number of Vijay, I must make sure that he has not issued more than 5 books. In the cardinality constraints that we provided, we could not check that a person has issued more than 5 books. But now we can put in a predicate saying that the number of books which are issued by Vijay using SQL type structures, we can find out that that must not exist and must not exceed 5. This category of borrower, MTechs may not have more than 5 books, research scholars may not have more than 10 books, faculty cannot return a book, cannot take a book more than 1 year. Things like this we can always put in, and we can, in general, we can have any arbitrary predicate which must always hold. But there is a cost associated with each such definition of an integrity constraint. The cost is that this integrity constraint must be invoked during every operation, and whenever we invoke it during every operation, there is a time spent in checking this integrity constraint. That is why I mentioned here that effectively also means efficiently. The efficiency must be taken into account when we define such constraints. So, while in a general relational model we can define a general relation for every consistency and constraint check that we want, there is a cost associated with it. That is, during every database updation, these constraints will jump up, come into the picture, and we will have to start checking all of them. And if we mention arbitrary predicates, that means a huge set of programs will start operating. So, what we want is we want to define them in such a way so that the checks will be a more number of checks can be done easily, and we leave the complex checks, those which cannot be done by simple means, to the expression of general predicates only. So, we now must have in a relational model mechanisms for specifying the constraints which must be checked in a formal manner, so that the database can be checked from time to time quickly. So, we will discuss some of the schemes which are available to do this. Many of them are borrowed directly from the ER model, and some of them are new. We shall see them now one after another. Useful schemes for specifying and checking integrity constraints on a relational model. The three well defined and well known such constraints are the domain constraints, the referential integrity constraints, and the constraints which are called functional dependencies. We shall now study them one by one and see what each of them mean. First, we will pick up the domain constraints. Before proceeding into that, as always, we will look back to the example database which we are seeing. The book, the library database having the book with accession number, year of publication, title, user with card number, borrower's name, borrower's address, and supplier with supplier name and supplier's address. The borrow relation has accession number, card number, date of issue, and the sub relation has got accession number, supplier's name, price, and date of supply. The first thing in the concept of domain constraints is the definition of domains of each attribute. For example, we will define the domain or the type of accession number, and we can define it in many ways. We can define it as a character string of type 20, depending on the size which is required, or a character string of type 10, of length 10. We can specifically say that it can be an alphanumeric string, so that exclamation and other special characters do not come into the picture. And automatically, whenever we enter a new accession number, or whenever any updation or insertion is done, this type will be checked. And if the type is violated, immediately an error message will be flashed, and therefore at entry time you can catch this instead of doing it during processing. Now, it is very crucial to accurately and correctly specify the type of an attribute, because that is the actual constraint which has to be done. Now, if in the library database the accession number are alphanumeric, then we will have to specify it that way. If it is an integer, then we will specify it as an integer, and though alphanumeric numbers take in integers, we will specify it as an integer. More accurately, we will specify it as an unsigned integer, which is a positive integer. And if you have some idea of the limits to the accession numbers, to the range in which your accession numbers will work, then you specify the range. You can specify a range type, range, that this accession number will be from this to this. So, the accuracy of specification of the domain of the attribute is very crucial. It has to be done keeping into mind the database, its future and other aspects as well, but though it looks a very trivial issue, it has to be done very, very carefully. Let us take the attribute date of issue. In all database systems, we will notice, those who have used it, you have a date type. A date type is a predefined type provided here. You can also create your own structured types and make a date type which will take the date as dd, mm, yy or mm, dd, yy according to the format. And nowadays, I would like to point out this YY is causing a lot of problems because of the turn of the century. Therefore, those who have had dd, mm, yy and saved space doing dd, mm, yy are now facing problems with this YY. So, the accuracy of specification of the attribute is the first and very important thing in the domain constraint. Along with these, you can specify some additional constraints which must hold on the domains. For example, you can specify here, if the library was started from a particular date, then date of issue at every moment must be greater than or equal to some particular date. So, this check must be there. Somebody puts in a date of issue which is absolutely atrocious. It may be a date, but it may be an atrocious date. And these may not always be, we may not be always able to put them in the, if we can put them in the range, then it is fine. Otherwise, we may not be able to put them in the range. Alright. So, a date of issue can be, an added constraint on the domain can be put like this. A better example is the following entity. Let us take an entity in the any relation which is got the salary of an employee in a particular department. So, the attributes are name, address, department, the gross salary, deductions and salary paid. And each of the domains is defined. In spite of specifying these domains, we may have some inter-attribute constraints which must be satisfied on the domains of the attributes. One of them is, for example, the gross salary must equal the deductions plus the salary paid. Now, this constraint must always hold. This cannot be specified by the type declarations, but this can be specified by additional domain constraints. So, simple domain constraints which when put into the database will automatically check and do it very quickly. Instead of this, if you wrote in a big predicate, then the overheads of evaluating that predicate would come into the picture. On the other hand, This one is a simpler check. So, we have done domain constraints. The next topic, and a very important and a crucial conceptual idea of specifying constraints, are the referential integrity constraints. We will pick up two cases to highlight the problems that can occur if referential integrity constraints are not taken into account. The first case, case 1. Let us see, the book relation has got accession number, year of publication and title. The borrow relation has got accession number, card number and date of issue. Somehow we may be knowing that this is the primary key here and this is the primary key attribute here. That is fine. But let us look at this situation. There is a tuple with accession number 57326 in borrow, but there is no tuple with accession number 57326 in book. Now, borrow is a relation which is known to be those books which are issued by people having these card numbers. So, a person who has issued a particular book, if he has issued a particular book on a particular date, and the accession number of book is there in the borrow relation. And if there is, though both are primary keys here, the same primary key is here, if there is a book here with accession number 57326 in borrow, there must be a book with accession number 57326 in book, because book is all the books in the library. So, this situation is inconsistent. Let us see the alternative situation. Case 2. Book accession number. There is a tuple with accession number 57326 in book, but no tuple with accession number 57326 in borrow. The question is, can this happen? This can definitely happen. This can happen because that book may not have been issued to anybody. That book may be in the library. So, two syntactically exact situations, one is inconsistent and the other is consistent. This is not the only case in our example. This will come up in several other cases. There cannot be an S name here which is not existing in supplier. There cannot be a card number here which is not existing in user. So, these things are important and these things need to be checked, because otherwise you will have some very peculiar situations which will arise. These constraints are specified by the concept of referential integrity. Now, let us see what referential integrity means. It is also called referential integrity or subset dependencies. It is denoted by this expression, this relational algebra expression. Let us see it with the example in the inconsistent situation before we see the formal definition. We say that accession number is a foreign key referencing book. Accession number is a primary key of borrow, that is all right. But accession number is also a foreign key referencing the relation book, which means that in the relation book, for every accession number which exists in borrow, there must be an element, a tuple in book having the same accession number. Therefore, a foreign key will always be the primary key of the referencing, the relation which is referenced. If an element is a primary key here, under normal situations, it will be the key attribute of the referenced relation. So, whenever we say that accession number is a foreign key referencing book, we mean that this situation will never take place. Formally we say, let R1, this is the relation name, and capital R1 is its relation scheme or the set of attributes, and R2 with capital R2 be two relations. Suppose alpha, which is a subset of the attributes of R2, is a foreign key referencing the primary key of R1. That is, we have got two relations, R1 and R2, and alpha is a subset of the attributes of R2, and it is a foreign key of R1. Since it is a foreign key referencing R1, it must reference the primary key. It is sufficient to reference the primary key instead of all the attributes. Therefore, what does this mean? The all tuples, we do a projection on alpha of R2. So, we get all tuples of R2 having the attribute values corresponding to the attribute alpha. Each of them must exist in R1. Therefore, the projection on the key attribute of R1 must be a superset of the projection of alpha of R2. So, in our situation, we will have pi of accession number of borrow must be a subset of pi of accession number of book. All the accession numbers of borrow must be a subset of all the accession numbers of book. This is how we simply specify the referential integrity constraints. So, this is the definition of referential integrity constraints. Now, how is this to be checked? We will see very soon. Before that, we quickly see how SQL defines such. In SQL, we saw we have the create table command. To create any table, we have seen in the previous day, we have got the command create table. Attribute create table book, attribute and type. Attribute and type. Maybe we have got a year type defined in the system, and the other one is title. We saw these are the simple, this is the simplest mechanism by which we can define the constraints. So, this is how we define some of the domain values. Additionally, we can say that this is not null, this cannot be null. We discussed views, we discussed that some attributes may not be specified. For example, you may get a book and you may not be able to really find out the year of publication of the book. Many libraries have got old and very vague types of books where you do not have the year of publication. But obviously, accession number of the book cannot be null. Neither can the title of the book be null. Otherwise, how do you define the book itself? So maybe you will be able to say that these two fields should be non-null, and every time you insert or update any field, you will check whether these are null or not. Other than this, you will have to specify what is the primary key. So we are specifying the constraints, we specified the attributes, we specified the types, what is null, what is not null, and what is the primary key. Similarly, you can specify user, which will have card number, borrower's name, borrower's address. Let us see and try to specify the borrow relation. We have got accession number, which is a type character, then we have got card number, which is another, say, character 8, and we have got date of issue, which is of date type. And we have got primary key, accession number. Additionally, we will have to now define the foreign keys. What are the two foreign keys here? Accession number is a foreign key referencing the relation book, and card number is a foreign key referencing the relation user. Therefore, we will say and we will also have to specify the non-null attributes. For example, we cannot expect the accession number, nor can we expect the card number to be null. Maybe the date of issue may by chance be null, that may be acceptable, but obviously these two should not be null. You do not know what book has been issued, and you also do not know who has issued the book. None of them may be acceptable. So we have got to specify these, and these. So that we can do for all the attributes. We specify the type of each attribute, the primary keys, and which is null, which is non-null, and we specify all the foreign keys. Next, we will see what we do with this integrity constraint during database modification. Suppose you have the constraint like this. What does this mean? That alpha is a subset of the attributes of R2, and alpha is a foreign key referencing R1. That is, pi alpha of R2 is a subset of pi of the key attribute of R1. So now let us see what we do in each situation. So we have got this constraint, we have got our constraint, that is we have got two relations R1 and R2, and in R2 we have got a set of attributes alpha which is a foreign key referencing R1. Which leads to this subset dependency. What will we do during insert? If any tuple of T1 of R1 is inserted, there is no problem. If we insert a new tuple in R1, there is no problem, because we don't have to check anything with respect to R2. But if we add any tuple in R2, we have to see that for the attribute alpha, there is a corresponding tuple in R1. That is very simple. That is, whenever we insert anything here, we check that for that attribute alpha in T2, that attribute must be an element of pi k of R1, because this dependency must hold. This subset dependency must hold means if T2 is inserted in R2, we must ensure that the attribute alpha corresponding to T2 must be an element of R1 with the key attribute taken out. Key attribute is sufficient because that defines uniquely all the attributes. The next is delete. Now, if an element T1, if an element is deleted from R2, there is no problem, because we don't have to check anything. But if an element is deleted from R1, then we have to ensure that there is no tagged element left behind in R2. For that, if T1 is deleted from R1, we must ensure that all tuples of R2 which satisfy T1 for the primary attribute k, which is same as the attribute alpha. The attributes alpha is same as the alpha attribute set, and k attribute set are same. Therefore, this, if we select out those tuples which have alpha equal to T1 of k, that set must be empty, because if that set is not empty, we will have the inconsistent situation of that is, we delete an element from the relation book and we still have some accession number in borrow for that book. That should not happen. That is, we must not delete an element from the database in the relation book which is being currently borrowed by somebody. That means some mischief is going on. So this check must be made. So during insertion this check must be made, and during deletion this check must be made. Lastly, we come to the concept of updation. What do we do during updation? Let us see. If we modify a value of R2, that is, we modify a tuple in R2. Now, as we said before, updation can be looked as a combination of deletion followed by insertion. So if we look at updation to be deletion followed by insertion, if an element is deleted from R2, we have no problems. When an element is inserted into R2, we do a check. So when a tuple T2 is updated in R2, we will do the check corresponding to insertion. Coming to R1, if any element is deleted from R1, we have to do a check. But if an element is inserted into R1, we do no check. So when an element in R1, when a tuple in R1 is updated, we do a check corresponding to deletion. That will be sufficient to do updation. Therefore, if T2 is updated in R2 and update modifies values for the foreign key alpha, if it does not modify values for the foreign key alpha, then nothing needs to be done. But if it does modify values for the foreign key alpha, then the check is similar to insert. On the other hand, if T1 is updated in R1 and update modifies values for the primary key, if it does not modify values for the primary key, again nothing needs to be done. But if it does modify values for the primary key, then the check is similar to deletion. Therefore, now the checking for insertion and deletion can be used for updation. So by defining the foreign key relationship, we can check what are known as referential integrity. So referential integrity, other than the domain constraints which have to be checked, referential integrity is another set of constraints which have to be checked at every point of time during insertion, deletion and updation. And the specification of this is done by the foreign key relationship, the foreign key specification. We've seen how it is done in SQL, and we've seen how it is checked at every step. The next and very important concept of constraint is the concept of functional dependencies, which we shall see in the next class.